So good afternoon, everybody. For those of you who do not know me, I'm Milan Kulkarni. I'm the Michael and Catherine Burke Head of the Elmore Family School of Electrical Computer Engineering, a nice long title. But today, I'm not the main attraction. Our main attraction is our guest, Shanhui Fan. I am not actually going to introduce him. First, I'm going to tell you a little bit about why we're all here, and then I will introduce Ali, who will introduce him. So we're here for the Purdue Engineering Distinguished Lecture Series. This began in 2018. And the goal of this lecture series is to invite world-renowned faculty and professionals to Purdue Engineering in order to encourage thought-provoking conversations and ideas with faculty and students regarding the grand challenges and opportunities in their fields. Besides presenting a lecture to a broad audience of faculty, graduate, and undergraduate students, they're going to engage in an interactive panel with Purdue faculty and students. So we'll have the talk followed by the panel. And to introduce our guest, I would like to bring up to the stage Ali Shakouri. He is our Associate Dean for Research and Innovation. He is also a professor in ECE, and he is going to introduce Shanhui.
Thank you. Good afternoon. It's my pleasure to introduce my old friend, Shanhui Fan. He's the Joseph and Hon Mai Goodman Professor at the School of Engineering and a Professor of Electrical Engineering and a Professor of Applied Physics by courtesy at Stanford. He is also a Senior Fellow of the Perkord Institute for Energy. Just a quick anecdote, Joe Goodman was one of the icons at Stanford with the Fourier optics and so on, so he's very well suited to Shanhui to have his title. He received his PhD in '97 from MIT, working in condensed matter physics, theoretical condensed matter physics. His interests are in the fundamental areas of nano-photonics, especially photonic crystals, plasmonic structures, and metamaterials, for which we have quite a bit of activity here at Purdue, so really look forward to see how we can better connect and collaborate. He has been looking for the application of this structure both for energy and information technology, which is very exciting. He has published approximately 700 journal papers, 400 plenary, keynote, and invited talks. So I guess today we'll add 0.25% to his invited talks. He has 70 US patents, co-founder of 2 companies, one in commercializing high-speed engineering computation, and the second one on the radiative cooling technology. He have received numerous awards early on, the NSF Career Award, the Packard Fellowship, the National Academy of Sciences Baker Award, Adolph Lamp Medal from Optical Society of America at the time. That was for the junior, but of course, over the years, he have received the Wood Prize from Optica. He has been a Vannevar Bush faculty fellow from U.S. Department of Defense, and is currently a member of National Academy of Engineering and a fellow of multiple societies, IEEE, Physical Society, Optica, and SPIE. Please join me in welcoming Shanhui. Thank you.
Well, thank you. Thanks, Ali, for the very kind introduction, and it's great to be back here. I put this title, The Opportunity of Photonics at Nanoscale, a year ago when I accepted this invitation, and at the time I really had no idea what I was going to talk about. And this week, when I was preparing for this talk, I realized there's going to be a panel afterwards, which has a much better title than the one that I have, and also with a set of very distinguished professors here who have thought very deeply about these big questions associated with nanophotonics. So I thought that based upon this title of the panel, I would just address these 3 aspects of nanophotonics, from energy to AI to quantum. So here is a brief outline of my talk. On the energy side, I will talk briefly about our work on radiator cooling. And on the AI side, I will talk about some of our work in thinking about optical neural network. And finally, related to quantum technology, I will talk about some of our thinking in creating arbitrary Hamiltonians in the synthetic frequency dimension. So let me start with the first part on radiative cooling related to energy applications associated with nano-photonics. And if you need to think about energy technology, you need to think about thermodynamics. And you need to think about the thermodynamic resource around us. For example, the sun at 6,000 Kelvin approximately is a great thermodynamic resource because it's high temperature, it provides the energy source. Now, photonics come in energy technology because all these thermodynamic resources fundamentally absorb or emit thermal radiation. Thermal radiation, hopefully, is a familiar concept. Perhaps the most well-known example is a light bulb. You take a tungsten filament, heat it up to a few thousand Kelvin, or 2,000 degrees or so, it will emit white light. So looking at this picture, what you immediately see is that the typical thermal radiation are broadband and wide angle. And there are also a number of fundamental constraints associated with these conventional thermal radiator. One of the exciting opportunity in nanophotonics is that all these fundamental constraints and properties need to be rethought about when you look at photonic structure. So here are some of the pioneering work. On the right is a work by Jean-Jacques Griffith, who showed that if you put in a photonic grating into a silicon carbide structure, you can have thermal radiations that are very narrow in angle. On the left is the work by Willy Padilla's group. He showed that if you have these gold nano antenna, I have the scale bar there, and you look at its emissivity spectrum, its emissivity is not broadband, but rather can be very sharply peaked. So these kind of unusual thermal radiation properties turned out to be very important in energy technology. Here, we are going to use this kind of capability to do radiated cooling, or in our slogan is to try to harvest the coldness of the universe. The argument is a simple one. If you look at basic thermodynamics, to get high efficiency of conversion from heat to work, you would like to have a low temperature heat sink. And most of our technology at the moment use the Earth itself as a heat sink, and that's at a temperature of 300 Kelvin. If you can instead use the universe as a heat sink at a temperature of 3 Kelvin, things will be very different. Photonics come in because we have radiative access to the outer space. So the black line here is a typical transmission spectrum of atmosphere. You can see that the atmosphere is highly transparent in the wavelength range between 8 to 13 micron. And this wavelength range happened to coincide with a peak of a 300 Kelvin blackbody radiation. That's a temperature approximately our temperature. So the point about this is that if you go out today into outside, now that you have sky access, we are at 300 Kelvin, so we will actually radiate thermal radiation through the atmosphere to the outer space. And that represents an inherent cooling mechanism. So one ought to be able to use this thermal radiation for cooling purposes. Now, of course, in spite of what I said about radiative cooling, if you want to do this experiment by walking out right now into the sun, you are not going to feel any cooler. The problem is a simple one. The sun is heating you up. So therefore, you will need to do more photonic design. And about 12 years ago, we published this theoretical paper trying to design a photonic structure for daytime radiative cooling. What we do is we design a structure that strongly reflects all the sunlight so that it doesn't get heated up by the sun, but it radiates strongly in the wavelength range of 8 to 13 micron. And so in our theory paper, we did a calculation and made two predictions. One of them is that if you build one of these things And if you put it outside with proper thermal insulation, you should be able to get sub-freezing temperature under the sun entirely passively. And also the cooling power of the structure, which is the amount of power that you need to bring in order to bring the object temperature back to the ambient temperature, and therefore the amount of heat that you're going to suck out from the surrounding environment exceed 100 watt per meter square. These theoretical predictions at the time look somewhat strange, but 12 years now, it has been demonstrated by a large number of experimental groups. Here is our demonstration, which was the first demonstration of daytime radiated cooling. You see pictures here, Ashwath Raman, who is now a professor at UCLA, and Lin Xiaozhu, now a professor at Penn State. What we are looking at is an 8-inch silicon wafer. And this wafer has a silver coating on top of it and dielectric layers on top of the silver coating. Together, they are a very good solar reflector. Average over the solar spectrum is about 96% reflectivity. On the other hand, in this structure, silica, which is the material of common glass, actually emits strong thermal radiation due to the oscillation between silicon and oxygen bound. And with the additional dielectric layer that we put in, the result is that it gives a selective emissivity peak in the wavelength range of 8 to 13 micron. So we test this on the roof of our electrical engineering building, which quite fortunate for us has a very nice flat roof for this kind of experiment. So we tilted the radiator towards the sun so that about 900 watt per meter square of power is incident upon the emitter. And in spite of the solar radiation incidence, the emitter or the structure has a temperature that's 5 degrees Celsius below the ambient air temperature. And this is done entirely passively with no energy input. So since then, there has been enormous amount of work, both by ourselves, but also by many, many groups here, many groups around the world on radiated cooling. I, in particular, should mention Professor Run here, who had done really outstanding work in radiated cooling pens, for example, some of the very impressive work. You can find these discussions in some of the reviews that we publish. But one of the commercial applications of the radiated cooling is to do air conditioning of buildings. And for that purpose, together with Ashwath Raman and also Eli Goldstein, and also my postdoc, we started this company called SkyCool System, aiming to deploy a radiated cooling system onto air conditioning of buildings. So here is one picture of one of these deployed systems on the rooftop of a supermarket in California. What we do is we have these radiated cooling panel, and underneath the panel, we have circulating water loop. What the panel does is it lowers the temperature of water below that of the ambient air temperature. Once you have that, you can feed those water into a water-based cooling power, and the result is substantial improvement of air conditioning system efficiency. So there are, in fact, quite a few startups in this space that are trying to bring various aspects of radiated cooling technology to the market. Here, I would just like to maybe show one of the recent further work that we have done in the space of radiated cooling. And the experiment that I show you is a rooftop experiment where the radiated cooling panel directly faces the sky. Now, that, of course, would be deployed on the rooftop of a building, like what I showed just now. On the other hand, if you look at most of these buildings, they are also vertical surfaces. And so for cooling technology, it will be interesting to study whether it's possible to use this vertical surface for cooling purposes as well. This actually brings additional challenges in optical design. So when you have a cooling panel face the sky, the radiation from the ground, usually the ground is hot, will be reflected by the back mirror and therefore does not contribute to the heating of the thermal radiator. On the other hand, when you have a radiated cooling panel in a vertical direction, it is going to see the radiation from the ground. So consequently, here, in addition to the usual requirement of a radiated cooler, you also need to suppress the absorption of emission from the ground. And therefore, one needs to design a selective emitter that is selective both in angle and in spectrum. And the way we do it, here is the structure that we come up. The structure has various components to it. It has a coating made of nanoporous polyethylene film. In this, here what you see is an SEM image of how the film look like at the micron length scale. These films has air holes on the size of several hundred nanometer. So they very strongly scatter sunlight. And as a result, a film like this looks white. It's a strong solar reflector. On the other hand, polyethylene is transparent for thermal radiation, so that things underneath it can radiate out. Now, what we put underneath the nanoporous polyethylene film is a sawtooth grating. The slanted surface is coated by silver to suppress the absorption of the emission from the ground. And the flat surface is coated by silicon nitride so that it still has strong thermal emission going to the sky. And so here are some of the measured solar and thermal spectrum, both as a function of angle and as a function of wavelengths. You can see for the solar, the reflectivity is completely red, so it's near 100% for all angle and for all wavelengths, which satisfy the reflection part of the requirement. For the thermal emissivity in the infrared wavelength range, you can see the emissivity going up is very high, but has very little emissivity going down, and therefore has very little absorptivity for the ground radiation. And moreover, is spectrally selective, again, in the wavelength range of 8 to 13 micron. And so here is the experimental setup. This is done by my former student, who is now the professor in Chinese Academy of Science, Professor Wei Li's group. So we compare 3 different structures put in the vertical configuration: a white pen, these are regular white pen that you have, a standard radiated cooler. These are now commercially available, so we actually bought it from one of the company in China. They are made out of polymer and silica microsphere, and that will give you, just like our early experiment, a few degrees Celsius below ambient if you put in a flat configuration. And then the last one is our own new design, this angle selective radiative cooler. And you can compare the temperature of the 3 structures, but instead I'll show you a picture first. So these are infrared camera image of the 3 structures around noontime. So red means hot and blue means cold. So just by looking at the infrared image, you can see that this angle selective radiated cooler is colder. And in fact, when you measure it, the white pen is above the ambient temperature. The standard radiated cooler also is above ambient temperature when you put in the vertical configuration because of this absorption of the ground radiation. The angle selective one, on the other hand, can still get to a temperature below the ambient air temperature. So I hope to use this example to show that there are still a lot of interesting engineering, optical engineering that you can do in shaping the thermal radiation side for many of the energy applications. So that concludes the first part of my talk. In the second part, I'm going to switch gear to talk about AI. There are many headlines on AI. Here are some of them. And the energy consumption of AI has always been a major issue associated with artificial intelligence. And these are old news articles, but you can see newer news article about, for example, trying to build nuclear power plant to drive a data center. So there's certainly an interest in trying to develop computational technology related to AI with lower energy consumption. For that purpose, it's useful to take a look at some of the standard algorithms. So these are the artificial neural network algorithm that's very widely used. And the textbook example, this would do, for example, hand digit recognition, where you feed the network with an image, and it will tell you what this image is. If you look at the underlying algorithm, this consists of a cascading of linear operation. It's a matrix vector multiplication where the vector initially can be just an image pixel itself, and then followed by nonlinear activation function, and then you repeat that many, many times. So this works, and there are two modes of operation associated with it. One of them is called inference. You put in the image, and the network tells you what the image is. Now, in order for the network to actually work, you need to train it. And the way you train it is you train this W. In other words, you pick the correct matrix element associated inside this matrix. And in order to do training, you would typically minimize a cost function as measured by the difference between the outcome and the intended outcome. So you get a cost function. You compute the gradient of the cost function with respect to the matrix element. You adjust the matrix element in terms of these gradient until this network works. So training usually requires many inference steps. Now, regardless of whether you're trying to do inference or training, you need to do many, many of these inference steps. So, and for our purpose here, it's useful to note that when you analyze these algorithms, the computational costs are dominated by the matrix vector multiplication. It's basically the linear transformation of the vectors on each stage. So that provides a very interesting opportunity for photonics, because in photonics, you do matrix vector multiplication all the time. You take any optical structure, you send in light, you look at the output light. The mathematical relation between the output and the input is a scattering matrix. It's relating the input to the output is a linear transformation. So any optical structure pretty much do matrix vector multiplication for you, essentially for free as far as energy is concerned. The only energy that's required in principle is the energy that you put in your input beam. So therefore, there has been a lot of interest in trying to exploit this in the neural network computation. So for on-chip silicon photonics, for example, there was a very well-known work. This came out of Marin Soliachik and Dirk England's group, where they build waveguide meshes. So these are on a silicon photonics network, on a silicon photonics chip. You lay down these waveguides, and then you put in phase shifter in some of these waveguides, and you control these phase shifter to implement various matrices that allow you to do neuromorphic computation. So now, as I mentioned, for this kind of thing to work, you need to train it. You need to pick the refractive index that you are going to put in on each of these phase shifter. And in the pioneering work in this paper, what they did is they built a computer model of this waveguide mesh. They trained the computer model to get the parameter, and then they implement the results of the computer model onto their silicon photonics chip. The problem with this kind of approach is that, in fact, it is very hard to get an accurate enough computer model for this chip in order to be able to train. And the challenge becomes harder and harder as these chips become larger and larger. So motivated by this, we proposed a few years ago this idea called in situ backpropagation. So the idea is to directly train the optical chip physically without building computer model. In particular, the standard training algorithm for neural network is what's called the backpropagation algorithm. So what we propose is a backpropagation algorithm implemented in situ on an optical chip, where we backpropagate the error signal physically through the chip, and then physically measure the gradient by interference measurement. The theoretical concept here is in fact very closely related to what's called the adjoint variable method that's very widely used in computational electromagnetics. So in computational electromagnetics, quite often you would like to do optimization of a device through inverse design. And as this very naive example, for example, you can imagine you have a source and you have a detector on the other side, and you would like to maximize the amount of power that the detector sees by adjusting the permittivity inside the black square there. So for that purpose, you need to compute the intensity at the detector, the gradient of that, the gradient of the intensity at the detector to the permittivity of every single pixel inside the design region. Now, you can do that by finite difference, and the computational cost will scale with the number of pixels that you have, which can be very, very costly because you can easily have thousands of pixels. Instead, in the adjoint variable method, you don't do individual adjustment of pixels. Instead, you do just two calculations. In the first calculation, you put a source at where the source needs to be compute the field distribution. Then you do what's called the adjoint calculation, where instead you put the source at where the detector is. Again, compute the field distribution. Once you have do these two computations, the sensitivity of the cost function to every single degree of freedom inside the structure can be done by an overlap integral between these two fields. So in doing so, you can get the sensitivity or the gradient in an arbitrary large dimensional space with only two simulations of the structure. Now, this idea is in fact very, very closely related to the backpropagation algorithm. And so what we do based upon this is to develop a physical way to get the gradient. If you look at the mathematical formula, you will see that the gradient is proportional to an overlap integral between the electric field in the forward calculation and the adjoint electric field in the backward calculation. And to get the gradient here, the gradient looks like an interference term, so all you need is an interference measurement between the forward field and the time reversal of the adjoint field. And based upon this, we propose this protocol to train optical neural network to try to measure the gradient. And this has three steps. In the first step, we just like in any inference step, we propagate the field through the network, we record the output. Once we get the output, you can compute the cost function. And in the second step, we do backpropagation, where we take the computed error signal, backpropagate into the network, again, record the transmission field. Now, in the third step, we time reverse the transmitted field, send both the original field and the time reverse of the adjoint field into the network. Then we somehow measure the intensity of the interference term at each of these phase shifter, and that gives gradient information. So that's a theoretical proposal a few years ago. More recently, in collaboration with my colleague, Olaf Solgaard and David Miller, we provided an experimental demonstration using, so this is a silicon photonics chip with all the electronic controls around it, built using a silicon photonics foundry in Singapore. I'll just highlight very briefly some of the aspects of it. In order to demonstrate in situ backpropagation, you need to be able to generate arbitrary input. And we have a way, this is built upon David Miller's early work, to take these waveguide mesh and generate arbitrary spatial mode that's coming out. You will also need to be able to determine the modal content of arbitrary field. And this is done by an analyzer where you adjust each of the phase shifter until an input mode gets completely routed into a single output waveguide. Once you have done that, then the information about that mode is entirely in the phase shifter, how you adjust it. And consequently, you also know how to do time reversal as well. Lastly, we would need to measure the intensity distribution inside the chip in the unit that we call matrix unit that does matrix vector multiplication. And this is done by within the structure near each of the phase shifter, we put in an additional grating coupler that couple just a tiny little bit of light in the vertical direction. And as a result, a camera image from the top looking at this chip while it is in operation gives you the field distribution or the intensity distribution at each of these phase shifters. And this image, as I show here, is in fact the gradient that we use to train this neural network. So this, I guess, concludes the second part of my talk on thinking about optical neural network, where I hope at least to give you an impression that there is actually a lot of opportunities in thinking about these photonic structure for in the context of AI hardware, in the context of AI hardware acceleration. Let me now go to the third part on what we call synthetic frequency dimension. I'm going to show a set of theory and experiment that are purely classical, but I think it has important implication for quantum technology as well. So when you think about quantum technology, when you think about a quantum circuit, you are trying to control the dynamics. You're trying to control quantum dynamics. And if you open a quantum mechanics textbook, they tell you quantum dynamics are controlled by programming the Hamiltonian. So this is one of those typical Hamiltonian where we talk about the coupling between different modes. And what you would like to do is to program how different modes couple together. And in physics, this has been very widely used. For example, in topological physics, if you open almost every one of these theory papers on topological physics, it's all about creating a Hamiltonian specifically to create certain unusual topological physics effect. It is, of course, also important in quantum physics because quantum dynamics is controlled by the Hamiltonian. And therefore, if you have a way to program this Hamiltonian, you can enable a wide range of quantum interactions. Now, we do nano-photonics, we do metamaterial. There are quite a few pioneers of metamaterial sitting in the audience here. One way you can think about how you design metamaterial is, in fact, in thinking about designing this Hamiltonian. Here's an image of a negative index material in the microwave wavelength range, and it's made of these split ring resonators. So one way you can think about the physics property of this system is you say, well, each of these splitting resonators have specific modes with specific properties, and then the coupling of these modes inside the material together, of the modes together, give you the properties that you want to. Now, it is quite common, therefore, to try to design a physical structure in order to create certain interactions. On the other hand, if that is the route that you take, then each structure, pretty much each Hamiltonian probably takes a new structure to create. So one thing that we've been quite excited in the past few years is to turn the complexity from real space to a synthetic space. In our case, it's to a synthetic frequency space. So in particular, what we do is we consider spatially a far simpler structure of a ring with a modulator, but we show that you can, in fact, generate very complex Hamiltonians associated with this very simple structure. And this has a long history. A ring with a modulator is what people use, for example, in active mode locking of lasers. And you can find this classic review article that talk about many of the formalisms that we use as well. But our intent is very different. So let me tell you a bit of the basic background of this idea. You can take a single ring resonator, and you would, in the absence of group velocity dispersion, it would support a set of resonances because light goes around and being the wave, the frequency has to quantize. And so the spacing between in terms of frequency between this mode defines what's called the free spectral range. It is reciprocal to the round trip time. Now, for a static ring resonator, these modes don't couple to each other. To couple them, what we do is to put in a modulator. A modulator is a device where you apply a voltage to a material, and as a result, as you vary the voltage, the transmission can change. So therefore, you can get the transmission to change as a function of time. And in particular, we can design a transmission where the phase of the transmission varies sinusoidally at a modulation frequency omega m. Now, in this case, when light passes through a modulator, it generates new frequencies. Consequently, if you choose the modulation frequency to be equal to the mode spacing, then it will couple the modes separated by a single free spectral range together. As a result, for such a modulated ring, a single cavity, if you modulate at a free spectral range, its physics is described by this tie binding model. Now you get a one-dimensional tie binding model. And one of the interesting things is that the phase of the modulator shows up as the hopping phase between the nearest neighbor mode. And that turned out to be an effective magnetic field for photon that you can use to create a wide range of topological physics effects. Okay, so I've told you a little bit of the theoretical background. Now let me tell you a little bit about the experimental background. So a lot of the physics, especially topological physics, is in band structure. In this system, as I mentioned, you have a Hamiltonian that looks like this, which actually is a periodic Hamiltonian. So therefore, it also has a band structure. This is just a regular tie binding model with a cosine-looking band for those who are in solid-state physics. Now, the interesting part about this band structure is the definition of a wave vector. In this case, we are talking about the dynamics of a photon along the frequency axis, because the frequency changes. As a result, the wave vector is describing the motion of the photon along the frequency axis. And therefore, it has to be a physical variable that's conjugate to frequency. And that variable is time. So the result is that if you do a time-dependent transmission, you can read off the band structure of the system. So the way we do it is we take a laser with a particular frequency, and we look at the transmission. Now, this is a modulator, so therefore, the transmission is going to vary as a function of time. And so as we do a measurement at a particular frequency, we change the frequency, and we do another measurement, and we repeat. As a result, we can generate this two-dimensional diagram with frequency on one axis and time, and therefore wave vector on the other axis. And this is what the band structure looks like. So this is a theoretical calculation. We then set up a experimental demonstration of this idea. This was done by Avik Dutt, one of my postdocs, who is now the professor at University of Maryland. So we have a fiber loop of a length of 13 meters. So it has a free spectral range of 15 megahertz. Inside, we put in a lithium niobate electro-optic modulator. This has a modulation frequency up to a few gigahertz, which is much larger than free spectral range. As you'll see, this turned out to be quite important for our measurement. We have a fast detector system, again, with gigahertz kind of response, so that we can look at time-dependent transmission. And we have a narrow line width laser where we can sweep the frequency so that we can take this frequency, take this time-dependent transmission at different frequencies. So here is a typical experiment. On the right is traces of transmission as function of time. Each of these curves correspond to a particular injected laser frequency. So as you can see, sometimes you have peaks, and these peaks move as your frequency changes. And if you collect all the data on the right into a two-dimensional diagram that you have on the left, Now you recover this band structure of the system. And here it looks like a very nice looking cosine function, just like your usual tie binding band. So here I show you an example of creating a one-dimensional system in the ring undergoing modulation. It turned out that you can create multi-dimensional systems as well in a single ring. And the way you do it is that you take advantage of the fact that the modulator can be entirely electronically controlled. So this is really just what you control is just voltage as a function of time that you put on the modulator. So consequently, you can choose pretty much any waveform that you ever care about and put on the modulator. For example, instead of having only one modulation tone with single modulation frequency at the free spectral range, as I've just demonstrated, you can also put in another modulation tone, which is an integer multiple of the free spectral range. This creates a new model. And you can look at in one dimension, you will have a long-range coupling. You can plot the same model in a different way to see that this corresponds to, in fact, a two-dimensional system. And one of the dimension is infinite. The other one, the size, corresponds to this m here, the integer multiple of free spectral range. So as a result, you can create a two-dimensional system this way and read off the band structure from here. And it's not too hard to see that any dimension essentially can be done this way. So I've shown you a set of theoretical and experimental background associated with this synthetic dimension concept. In the final, maybe a few minutes of my talk, I'll just show you just one recent example where we use this as a platform to demonstrate some interesting new physics effect. And this is associated with what's called the non-abelian gauge field. So non-abelian gauge field is a gauge field that describes the interaction of quantum particles with spins. And physically, when you apply a non-abelian gauge field to a particle with spin, what you have is a direction-dependent spin rotation. And this is important in physics because it is the language of fundamental particle physics. All fundamental interactions are described this way. And the theoretical importance of this non-abelian gauge field therefore motivates many people, including us, to try to develop an experimental platform so that you can try to explore some of the physics. Obviously, you can explore non-abelian gauge field physics inside a nucleus by studying quark, but it's not a very engineerable system. So it would be interesting to develop other systems that has non-abelian gauge field as well. So with this in mind, in fact, this is also of theoretical interest. We consider the SU2 lattice gauge field model. This is a model, it's a tie binding model where each side is a spin 1/2, so therefore has two states. And this particle with spin can hop from one side to the other, and as it hops, the spin can rotate, and that manifests this gauge potential. The non-abelian nature here comes in when you have different pathways that you give different outcomes. So in this case, imagine that you have a particle hop from the lower corner of that color square to the upper right corner of the color square. It can go through the red parts where you hop up first and hop to the right, or it can go the other way as indicated by the green line here, where you hop right first and then hop up. Now, in these cases, the two pathways correspond to two different spin rotation. And if this spin rotation doesn't commute, you will have a non-abelian gauge potential in the system, and therefore has non-abelian gauge physics. So one question then is what exactly is the manifestation of this non-abelian gauge physics in this system? For that purpose, you can diagonalize the Hamiltonian, go to momentum space, and then you will get a band structure as indicated by the equation below. And you can plot this band structure. What you see is that if you have a non-abelian gauge potential, the AX and AY gauge potential do not commute, then the band structure actually exhibit Dirac point at time reversal invariant momenta, for example, at the center of the first Boolean zone. In photonics, Dirac cone is not that uncommon. People can see that in graphene. There you have a Dirac cone at K point, but it turned out that the K point itself is not time reversal invariant. People have also tried to get a Dirac cone-like structure at gamma inside the Boolean zone center, at the Boolean zone center. But it turned out all those constructions, in addition to the Dirac cone-like structure, has additional flat band, and the overall structure is topologically trivial. It's not robust. So the Dirac cone structure at gamma, as we see here, is in fact rather unusual. You can show that that requires time reversal symmetry breaking, and that came out of the presence of these non-abelian gauge potential. Moreover, in this model, you can show that when those two operators don't commute, you get a Dirac cone. When they commute, you don't, and you get a nodal line. So as a result, there is this unique nature of the non-abelian gauge potential in this system manifested in this Dirac cone at the gamma point. With this as a theoretical background, we then went to do an experimental demonstration. So what we do is we again take this fiber loop architecture, and for the spin 1/2, we use the two polarization of the fiber. And to create the gauge potential, we put in polarization rotator, as well as a polarization splitter followed by individual electro-optic modulation of each of the polarization. And to create a two-dimensional lattice, the band structure I show you is for a two-dimensional lattice, we apply a voltage as a function of time on the electro-optic modulator in this time concatenated way so that it includes both free spectral range component as well as large multiple input, large integer multiple of the free spectral range. As a result, we were able to demonstrate the lattice SU2 lattice gauge field in this particular experimental platform. And here are some of the experimental results. In our band structure measurement, we sampled along lines inside the first Boolean zone due to our setup. So if this line sample through the center of the Boolean zone, the gamma point, you get a Dirac cone where the two bands cross. And this is something that we clearly see in our experiment. On the other hand, if we don't sample across the gamma point, as shown on the lower half of this slide here, the theory indicate that the system will be gapped. We see that experimentally as well. So we, in this case, provide a direct demonstration of some of the physics associated with the non-abelian gauge potential in an experimental platform that operates in the optical frequency range. So with this, I think I will summarize. I hope to give you an impression that you can do a lot in photonics. And light is such a fundamental aspect of nature that touch upon so many different technology. So new ways to manipulate light is certainly to have an impact in many different technological areas, as well in some of the fundamental science exploration. And there's something that I'm certainly very excited about, and I look forward to further discussions with you guys. Let me stop here.
Do you have time for questions? Yes, please.
A very nice talk. So for the optical neural network works. So I know that the weighted of the neural network can be continuous, but the refractive index can only be chosen a certain material. So how would you deal with that one?
So in the setup that we have is also continuous variation. These are applying either a voltage or in our current experiment, it's a thermal optics experiment, so it's changing the temperature. So the index vary in that range roughly linearly either with voltage or with temperature. So you actually get a continuous variable as well.
Questions? Maybe I can ask a quick question. In the second, in your second optical neural network, it was quite interesting. By just imaging, you could get information about how the fields. But I'm curious, this is a 2D structure. When you do vertical imaging, what are you actually measuring? Is it stray field? What is the light that you're measuring from the top?
Right. It's measuring the intensity of light at each of the phase shifter. So the setup is that we have these phase shifter, and then in the vicinity of the phase shifter, we put in a little grating coupler. So the amount of light that gets scattered in the vertical direction is proportional to the intensity inside these phase shifter. And that is a gradient that we actually need in order to train this network. Yeah. Sorry.
Thank you very much. A very nice talk. So for the first part, in the vertical wall,
Yeah.
so is there any thickness constraint on the top coating where you need not to block the emissivity from the bottom layer, right? So usually the solar reflective coating, they can be pretty emissive. Do you need to use IR transparent material, or its thickness allows to be transparent?
The material we use there for the top coating is IR transparent. So polyethylene turned out to be one of those materials that are transparent. So in fact, polyethylene is like what you do in plastic wrap in the kitchen. So the thickness of those are on the order of tens of micron. And for that kind of thickness, they are typically fairly transparent in the thermal side.
So the solar.
Yeah.
So for tens of microns, would the solar reflectance be somewhat kind of a compromised? Usually we need a few hundred microns to get the best,
yeah.
right?
Yeah, so I should have mentioned that for nanoporous, it's hundreds of micron.
Yeah.
Yeah, but the IR can still come up in that case.
Yeah, yes. Yeah. Okay, thank you.
Yeah.
Thank you for the very nice talk. When I was going to graduate school at MIT, I heard my professor say, electron wavelengths are very small, but photon wavelengths are very large. So working with photons, you can never miniaturize things to the level of electron integrates the circuits. So your gadgets are still pretty large compared to electronic gadgets. What is your comment on that?
That's a very interesting observation. Certainly, there has been a lot of interest in trying to develop nanoscale optical devices. In what I show, some of the structures, the feature size is on the nanoscale. The overall device is not. One thing I would say concerning this concept of electrons and photons, I would say that they are good for very different things. The typical statement is that optics or photon is very good for communication, for sending information from point A to point D and to route those information. And the useful optical device in reality are almost always this kind of devices. So if you look at our optical neural network, for example, this is in fact the same device that people use in silicon photonics to communicate information from point A to point B. There it makes sense to add additional functionalities associated with it. I don't think it makes sense in many situations to completely reproduce the functionality of electronics with photonics. And many people have tried, and I'm not sure that has been a very fruitful direction.
Okay.
I could very much offend large number of people sitting here, but I think so. I think when we compare photonics and electronics, it's important that they really do different things. And in the end, the kind of system that works combines both. So in our optical neural network, there are large amount of electronic control associated with that network. For example, we need to program the phase shifter, the refractive index. All those things are electronics. And in our synthetic dimension work, one of the power of this is in fact an electronic control layer that allow us to program this voltage as a function of time to create Hamiltonian. So almost any successful system that you come to see are a combination of optics and electronics.
Hi, very nice talk. I have two questions. One is about the thermal modulation. How fast can it go?
Thermal modulation is not fast. Sometimes you can talk about maybe a millisecond kind of scale. But there's nothing that restricts the neural network to use thermal modulation. We do it because it's simple.
Okay.
We do it because it's simple. Electro-optic modulation can get to gigahertz.
Yeah. So my second question is about the radiative cooling for with an angle. Right? Typically, it's fabricated in the clean room, right? What do you envision for the future mass production of those devices?
Many radiative cooling things are not fabricated in the clean room. I think I can refer to Professor Ran here, who make radiative cooling pens, are not fabricated in the clean room. In this particular case, the grating is fabricated in the clean room, but the feature sizes are very large. These are a few micron feature sizes. So even this, you can fabricate fairly cheaply in a it doesn't take state-of-the-art lithography at all.
Thank you.
Yeah, here.
Thank you, Professor Fan. Really nice talk. I'm sorry, I personally don't work with photons, so I'm not sure whether I fully get the point of your talks, but I do have two questions. The first one is about your last project of obtaining the band structure.
Right.
Because from my knowledge, obtaining band structure, especially detailed band structure, is quite hard. People usually use APIS or things like that.
Right.
But is your technique applicable to like all types of materials, or is this like only designed for specific types of materials?
Okay. So it's a very good question. First of all, this is a technique only that we designed just for this system. So we don't intend to present this as a general band structure measurement technique. I should say though that conceptually is very similar to APIS. In the APIS experiment, you do an angle resolve electron scattering experiment, and you vary the angle, and you look at the energy spectrum that tell you the band structure. In our case, instead of doing angle resolve measurement, we do time resolve measurement, because in our system, time is the wave vector. So conceptually, they are actually very, very similar to APIS.
You had a question on this side?
Yep. One last one, maybe. So in a synthetic dimensional studies, do you see any way of simulating anisotropic exchange type of interaction, not just simple hopping type of interactions?
I think so, yes. In fact, in this SU2 model, which is a spin 1/2 model, there's a lot of control of the A. So the X spin and the Y spin certainly need not to hop in the same way. So those kind of Hamiltonian can be straightforwardly done.
Very good. So I guess it's a time to thank Professor Fan.